Yes, welcome everyone to a new talk at the virtual seminar on geometry with symmetries. And today it's my great pleasure to introduce Alejandro Tolcachier from Córdoba in Argentina. And Ale will be speaking about special Hermitian metrics on products of Sasakian manifolds. So up to you. Thanks.
Okay, thank you, Ramiro. And first of all, let me thank the organizers for inviting me to give this talk in this seminar. It's a pleasure. And this talk is based in a recent joint work with my PhD advisor, Adrián Andrada, also from Córdoba. This is a paper which we submitted to arXiv a few weeks ago. So please feel free to interrupt me in any moment and ask a question. Okay, so the idea of the talk is to study the Hermitian geometry of a two-parameter family of Hermitian structures, JAB, GAB, on the product of two Sasakian manifolds, S1, S2. So to do that, first I will review the definition of Sasakian manifolds, and I will introduce a few properties about them. Then I will review this construction of Hermitian structures in order to then study when these Hermitian structures are, in some sense, special metrics, namely balance metrics, locally conformally Kähler metrics, strong Kähler with torsion metrics, or k-Gauduchon metrics. And finally, we will study the associated Bismut connection to this Hermitian metric. And as a consequence, we will give examples of Calabi-Yau with torsion manifolds. Okay, so we start by recalling some definitions of almost contact geometry, which happens only in dimension odd. So an almost contact structure on a smooth manifold of dimension odd will be a triple given by an endomorphism phi of the tangent bundle, a vector field psi, and a one form eta related in the following way. Phi squared is equal to minus the identity plus a term involving eta and psi, and eta evaluated on psi is equal to the constant function 1. And this equation implies that the vector field psi is in the kernel of phi, and the image of this endomorphism phi is in the kernel of eta. So in this setting, when we have a structure like this, we can split the tangent bundle of the manifold as a subbundle D, which is the kernel of eta, and the line bundle L, which is generated by the vector field psi. So we can think an almost contact structure as phi is like an almost complex structure in the subbundle D, and we have this extra direction psi, and eta is like its dual form. Okay, so when we have an almost contact manifold, we can take the product with R, which is even dimensional, and we can define naturally an almost complex structure, J tilde, given in this way. Here we are thinking, we are using the notation of sum for the product instead of ordered pairs. And essentially, J tilde on the subbundle D is the endomorphism phi, and it takes the vector field psi to dia dt in R. So when this almost complex structure is integrable, the almost contact structure will be called normal. And this is equivalent to a certain tensor m phi to be 0, where this tensor involves this bracket phi phi, which is the nine-noise torsion defined very similar to the tensor in almost complex geometry, to the nine-noise tensor. So now we add a Riemannian metric, and we will have an almost contact metric structure on a dimensional manifold. If we have an almost contact structure and a compatible Riemannian metric in this sense. So phi is not orthogonal because we have this term, but using this equation, one can see that phi is skew symmetric everywhere on the manifold M. So we can define a fundamental to form capital phi as usual in complex geometry. And then a Sasakian manifold will be a normal almost contact metric manifold, satisfying that these two fundamental form is exact, and moreover is equal to the derivative of the one form eta. So it is known that Sasakian manifolds are the most important class of almost contact manifolds because of their close relation to Kähler manifolds. Indeed, one of these manifolds is Sasakian if and only if its Riemannian cone equipped with the almost complex structure we saw before is Kähler. Here I put in a lemma some very standard and well-known properties of Sasakian manifolds, which will be useful for us. Basically, in a Sasakian manifold, one can have a formula for the Levi-Civita connection associated to G, provided that one of the vector fields is the vector field psi. And moreover, we have a formula for the tensor nabla phi. So yeah, this is the properties that are useful to us in the sequel. And now with this, I will review the construction of these Hermitian structures. And this is due to several authors. The original idea started with Calabi-Ekman, with Calabi and Ekman in the 50s. They constructed a two-parameter family of complex structures in the product of dimensional spheres. And then Morimoto worked in general in any almost contact manifold, but he did not use these two parameters AB, but only A equal to 0 and B equal to 1. And then in works by Tsukada and Watson, indeed appear not only the complex structure JAB, but also the metric GAB. So the construction goes like this. Start with two almost contact metric manifolds, and then for real numbers AB be different from 0, we can induce an almost Hermitian structure JAB, GAB on the product of the manifolds. In this way, we have JAB and GAB. So it's an exercise on quadratic forms to verify that this metric is indeed positive definite. And well, this J is orthogonal with respect to G. G is a Riemannian metric, and J square is minus the identity. So this structure is really almost Hermitian. We can note that for the metric, for instance, if we restrict to the first factor, the metric is equal to G1, the original metric. And in the second factor, when we restrict to the distribution, the subbundle, sorry, D2, the metric coincides with G2, but modifies the length of Xi2 by a factor of a squared plus b squared. Also, Xi1 and Xi2 are no longer orthogonal whenever a is different from 0. And it is easily seen that this metric is the product metric of G1 and G2 if and only if a is 0 and b is equal to plus or minus 1. Moreover, to do some computations later, one can work with this orthonormal local frame, which has is Xi1 JAB of Xi1, which is not Xi2, but a combination of the two instead, and then these I's and F's, which are local sections of D1 and D2 respectively. The Morimoto's original construction, as I said, was for A equal to 0 and B equal to 1. And here, J01 of Xi1 is Xi2 because the other terms vanish. And the metric is the product. Morimoto in the 60s proved that if we have, without the metric, just almost complex structures and M1 and M2, then this almost complex structure in the product is integrable if and only if we start with normal almost complex structures. And then in the work of Tsukada, he says that the converse holds for not only for 0, 1, but for every A, B, and R be different from 0 instead. So it's like we haven't checked the converse, but the important thing for us is like if we start with normal almost complex structures, then JAB is integrable, so we will have a complex structure. And an important thing is that the complex structure on the Calabi-Yau manifolds can be obtained in this way, taking this Morimoto's product, beginning with the usual Sasakian structures on each sphere. So from now on, in the talk, we will assume that the manifolds are Sasakian, and we denote MAB to the product endowed with this Hermitian structure, JAB, GAB.
Alejandro, can I ask you a question?
Yes.
The case on the product of spheres of all dimension, the corresponding Riemannian metric G sub AB, do you know if it's homogeneous on this product?
Homogeneous. We haven't thought of that, but probably.
It's a product metric, right? You said?
Yes.
Yes, it's a product metric.
No. For it's not the product metric for arbitrary A and B, right?
Okay.
Or I misunderstood.
I think you were asking 0, 1.
No.
So A and B.
No, in general.
Okay. No, we haven't thought of that, but probably.
Okay, thank you.
Thank you.
But the Calabi-Yau manifold, I mean, the metric is a product metric. You said this was Morimoto's construction, right?
Yeah, the original one.
Yes.
Yes.
The one in the example.
Yes.
Okay.
It's only 0, 1. Okay. So once we have JAB and GAB, since this is a Riemannian metric, one can compute the Levi-Civita connection to this metric in terms of the Levi-Civita connection of each term, and we obtain something like this. And in this paper by Lee, Park, and Sekikawa, they also compute the curvature tensor and the Ricci tensor associated to this metric. For us, in the sequel, we will compute the codifferential. So it's important to have the computation of nabla J in this case. So we obtain something like that. For instance, we have, when we put below psi1 or psi2, nabla J is parallel. Okay, so now we move to the study of special Hermitian metrics. As all must know, the most important and I think the most well understood Hermitian manifolds are Kähler manifolds, in which the fundamental two form omega in terms of the metric and the complex structure is closed. So for us, if we have MAB, we can compute extending each tensor capital phi1, phi2, and the etas to the other factor as 0. We can compute by definition, and we have this term. So when we apply D, since phi1 and phi2 are exact, since we are in Sasakian manifolds, we only have the derivative of this term. And now this is equal to 0 if and only if phi1 and phi2 are 0, but then the dimension of the manifold only can be 1. So we have that the complex dimension of MAB is equal to 1. So we will be interested in the non-Kähler setting. So from now on, we will assume that the complex dimension of the product is greater than or equal to 2. And the complex dimension is this number, M1 plus M2 plus 1. Okay. Essentially, since the topology of Kähler manifolds is well understood, and also since there are several topological abstractions for the existence of a Kähler metric, in the literature, recently there are several other conditions, weaker conditions than being Kähler, that have been introduced. So we will analyze these following other special Hermitian metrics for MAB. The balance, locally conformally Kähler, strong Kähler with torsion, and others like Asteno-Kähler, Gauduchon, and k-Gauduchon. We start with balance metrics, which have the study of balance metrics initiated with the work of Michelsohn in the 80s. So we have the definition. If we have an Hermitian manifold, the metric is said to be balanced if the derivative not of omega, but the power -1 instead is 0, which is equivalent to omega being co-closed, or the d omega is 0, where delta omega is 0, sorry, where delta is the codifferential associated to the metric. For instance, for Calabi-Yau manifolds, Michelsohn proved that they do not admit any balance metrics apart from the example of Morimoto. So they do not admit any balance metric due to homological reasons. And for our case of MAB, we could prove that this Hermitian structure JAB, GAB is never balanced, of course, in the non-Kähler setting, right? So the proof is simply a computation we can compute the vector delta J, which is dual to the one form delta omega, and we obtain this expression involving this simply expression. And well, for this we had to compute nabla J, right? With the computation we did in the previous slides. So from here, it's clear that this is 0 if and only if n1 is 0 and n2 is 0. And this case, we are not considering it because we want non-Kähler manifolds. Well, the case of locally conformally Kähler metrics, they were widely studied since Vaisman's seminal paper of the 76. We have the definition. The metric will be called locally conformally Kähler. Well, the same definition is telling us the definition. So if we have an open covering such that in locally in these open sets, the metric is conformal to a Kähler metric. And a good fact about that is that this information is encoded in the existence of a closed one form theta, satisfying this relation with the omega and omega. And this one form theta coincides with the Lie form, which is defined on any Hermitian manifold by this 1 over m minus 1 delta omega composed with J. And if theta is parallel with respect to G, then the LCK metric is called Vaisman. And for Calabi-Yau manifolds, would prove that they are LCK if and only if the dimension, if and only if one factor has dimension 1 and the other has dimension greater than or equal to 2. And in our case of MAB, we obtain something the same condition, and this LCK structure is Vaisman. And again, the proof follows by computing the Lie form. And well, we have all the ingredients. When we replace this delta omega, we have this term. So we replace the omega, and theta in the LCK condition, and we have an equality like this. Now, if we analyze the components of S1 and S2 in each term, this equation, we will get that every of these terms must vanish. So if N2 is different from 0, again, we have, for instance, that capital phi 1 is 0, so the dimension of S1 is 1. And similarly, if N1 is different from 0, then the dimension of the other factor is 1. So we have this condition in the statement, and well, the theta is parallel. This follows from the computation of the Levi-Civita connection we did earlier. Okay, now we move on to analyze the Hermitian conditions involves some operator called DC operator. Let's see how it is defined. Given a Hermitian manifold, we can extend the complex manifold to differential forms, the complex structure, sorry. If we have a P form alpha, we can define J alpha as alpha in level 0, and this J entering each component and then composed with alpha for a higher level. So this operator DC, which is real, is then defined by this formula. So it's -1 to the power of P and J with this definition, the dj alpha. Okay, and this is well known that the derivative of this operator DC is equal to 2i del bar, where these are the Dolbeault operators. Okay, so with this DC operator, we can define this other special Hermitian matrix. For instance, a strong Kähler with torsion, for short SKT, also called pluriclose in the literature, if del bar omega is 0, or equivalently ddc omega equal to 0. These metrics have deep relations with physics and also with generalized Kähler geometry. We have a steno-Kähler matrix introduced by Yau in the 90s. If ddc omega to the power of n-2 is equal to 0, here clearly this notion only makes sense for n greater than or equal to 3. We have a k-Gauduchon matrix for k in this range if this wedge is equal to 0, involving ddc and powers of omega. And these metrics were introduced in this paper by Fu, Wang, and Wu, and the generalized Gauduchon matrix, which is the case when k is equal to n-1, and in this case, this term vanish, so we have only this term. And well, Gauduchon metrics are widely studied since this renowned result due to Gauduchon that every compact Hermitian manifold admits a unique Gauduchon metric in its conformal class. And moreover, we have these inclusions, and every SKT metric, just by definition, is one Gauduchon, since k equal to 1, and then, yeah, so every SKT implies that, but the converse does not need to hold. And also, as steno-Kähler, of course, are m-2 Gauduchon. And when n is equal to 3, and the complex dimension, these three notions are equivalent. SKT as steno-Kähler and 1 Gauduchon. Well, for SKT metrics in the Calabi-Yau case, Cavalcanti established that S1 crosses 3 and 2 copies of S3 are the only Calabi-Yau manifolds which admit non-Kähler SKT metrics. And well, for our case of MAB, we obtain that this Hermitian structure is SKT if and only if the manifold is a complex surface, that is, the complex dimension is 2, or both manifolds, both Sasakian manifolds, have a dimension 3 and A is equal to 0. And well, again, the proof is follows by computing the operator DDC for our omega AB. We obtain something like this, and this metric is SKT if and only if this vanishes. So we have that this term must be 0. And from here, we obtain that phi1 squared is 0, phi2 squared is 0, and also this term involving phi 1 and phi 2. So for these phi's to be 0, the dimension must be less than or equal to 3. Of course, since we are in a non-Kähler setting, one of them must be at least 3. And if both have dimension 3, this is not 0, so A must be 0. And well, it is clear that these conditions make this 0, so the metric is SKT. And we can note that on the complex surfaces, these metrics are both SKT and also Vaisman. And well, this is also a consequence of results of Fino-Tardini and Belgun. We move now to Asteno-Kähler metrics, which were already done by Matsuo for these structures JAB, GAB, and he obtained that is Asteno-Kähler if and only if this condition holds. And later, Fino-Ugarte in 2013 proved that these Hermitian structures JAB, GAB is one Gauduchon if and only if, again, this equation holds. So it's if and only if it's Asteno-Kähler. And just as a remark, for any N1 and N2, such that, well, the complex dimension is greater than or equal to 3, and N2 is positive, when one can solve this equation and find A and B such that this equation holds. So there are values of A and B such that this metric is Asteno-Kähler. And what we did was to compute when these Hermitian structures are k-Gauduchon, we restrict k greater than or equal to 2 because Fino-Ugarte already done the one case. So we obtain first, we assume that the complex dimension is greater than or equal to 4. And then we obtain that is k-Gauduchon if and only if A and B satisfy now this equation. So what is this equation telling us is that if we are considering the Gauduchon condition, which is k equal to n plus 1, this condition always holds. So these metrics are always Gauduchon. And if we are considering another k in this range, the condition is equivalent to the condition of Matsuo, which is Asteno-Kähler. So we obtain this theorem. And okay, we had to separate the complex dimension 3 case just for the proof. And well, in this case, the only missing case, because k equal to 1 was solved, is k equal to 2. That is a Gauduchon matrix. And we obtain that this metric is Gauduchon. Okay, so this is everything with the metrics. So now we move to study the Bismuth connection. And just to motivate, as we are interested in the non-Kähler setting, another approach to better comprehend these non-Kähler manifolds is to consider connections, nabla, preserving the structure, so such that the metric is parallel and also the complex structure is parallel. So such a connection is called Hermitian connection. And it is a well-known fact that the Levi-Civita connection is Hermitian if and only if the manifold is Kähler. So if we are interested in the non-Kähler setting, we should consider other connections. And in this talk, we will consider the Bismuth connection. Bismuth proved that on any Hermitian manifold, there exists a unique metric connection, nabla B, such that, well, since it is metric, nabla G is 0, and also nabla B J is a 0. And this connection has one extra property, such that this 0,3 tensor, TB, contracting the torsion with the metric, is a 3 form. And this property is called that this connection has a totally skew symmetric torsion. So the Bismuth connection is the only metric connection such that J is parallel and the torsion is a 3 form. Okay, so it's known as Bismuth connection, and also in the literature is called KT connection or Strominger connection. And well, one can compute the distortion, and is given by this formula, dc omega, and this is equal to minus d omega, jx, jy, and jz. And moreover, another important thing is that we can compute the Bismuth connection in terms of the Levi-Civita connection plus this 1/2 of the torsion. So with this information, we computed the Bismuth connection associated to this Hermitian structure, G, in terms of the characteristic connections on each term. Sorry, the characteristic connection in each term, in each Sasakian factor, where here the characteristic connection is defined on Sasakian manifolds and also in more general, and satisfies that is the only connection, is the unique connection that makes parallel all the tensors appearing in the definition of the Sasakian manifold, and also has a skew symmetric torsion. So in particular, we obtain, for instance, that Xi1 and Xi2 are p-parallel, and moreover, one can see that theta is also b-parallel. For instance, if we take a Morimoto structure, A is 0 and B is equal to 1, so the associated Bismuth connection behaves like a product connection. Well, and in the last part of the talk, we will try to give some examples of Calabi-Yau with torsion manifolds as a consequence of our study of Bismuth connection. And well, the setup here is that since J and G are b-parallel, then the holonomy of the associated to the Bismuth connection is contained in UN. And if the restricted holonomy group of this Bismuth connection are contained in SUN, then following a terminology appearing in the paper of Grantcherov and Poon, and also Grantcherov, we will say that these manifolds are Calabi-Yau with torsion. Okay, and these manifolds have attracted plenty of attention. For instance, one can see these works from the 2000 until very recently, and they are related with the following. Of course, as in the Riemannian case, one can compute the Ricci tensor and the Ricci form associated to the Bismuth connection, like the Levi-Civita connection, as usual, contracting the curvature tensor with the metric. And well, the CYT condition, Calabi-Yau with torsion for short, is equivalent to this Ricci form being 0. So we will characterize when this Hermitian structure satisfy either Ricci B is 0 or rho B is 0, and use this characterization to give examples of CYT manifolds. I would like to point out here that in the proof of when this structure satisfies one of these, we use some formulas of Ivanov and Papadopoulos, which are independent from the Bismuth curvature tensor. So there is no need to determine, in this case, this curvature. These formulas relates this Ricci, for instance, with the Riemannian Ricci and the torsion of the Bismuth connection. And also we computed this rho B using this Ricci B. Okay, and to characterize these conditions, this family of special Sasakian manifolds appear, which are called Sasakian eta-Einstein manifolds. And here is the definition. A Sasakian manifold is said to be eta-Einstein if the Ricci, the Riemannian Ricci tensor, decomposes as lambda g plus nu, and this term involving eta. So, okay, and what can we say about this? We have on any Sasakian manifold this formula for computing the Riemannian curvature, where the last term is psi, and from this one obtain a very well-known property that the Ricci of psi x is equal to 2n eta x, and from this one can obtain two conditions. One is that these constants, real constants lambda and nu, the sum is 2n, the dimension, the 1 minus the dimension, and also that this condition is equivalent to the manifold being Einstein in D, in the subbundle D. Okay, so another consequence of this fact is that every eta-Einstein manifold has constant scalar curvature. Well, with this setting, we can state the result. So we computed the Bismut-Ricci tensor, Ric B, associated to the Hermitian structure JAB, GAB, and we obtain in terms of the Riemannian Ricci tensors, Ric 1 and Ric 2, and also we have these other terms, but note that this is exactly the eta-Einstein condition. So we obtain that the Bismut-Ricci tensor vanishes if and only if S1 and S2 are eta-Einstein, and these are the constants. The lambda is lambda 1 is 2, and lambda 2 is 2 times this factor, and well, the nus are simply the dimension minus lambda. And in particular, in the Morimoto's case, the Bismut-Ricci tensor vanishes if and only if the manifolds are eta-Einstein with these two constants. Note that here the constants lambda are equal to 2 in both cases. And in the next result, we analyze the CYT condition, which is the Ricci form equals to 0. And then, okay, now we assume this for the dimension, for the proof. Well, And also, okay, we have that the Ric B is equal to 0 if and only if these are equal to 0. And again, since phi is an isomorphism of D, we have that rho B is equal to 0 if and only if both Sasakian factors are eta-Einstein, now with these uglier constants than before. Okay, so if one of these two are 0, then the Hermitian structure is CYT if and only if the other factor is eta-Einstein with the appropriate constant. So in order to exhibit some examples fulfilling these conditions with these constants, we recall the notion of dihomothetys introduced by Tano. So we have a Sasakian manifold, and we can deform the structure with these new tensors as is a positive constant, such that this new deformed structure is again Sasakian. And moreover, if we consider an eta-Einstein Sasakian manifold, we can consider a d-homothetic structure, and we obtain again an eta-Einstein Sasakian manifold, now with these two constants. And we will say that a Sasakian eta-Einstein manifold is positive, null, or negative, whether if the constant lambda of Sasakian eta-Einstein is greater than -2, equal to -2, or less than -2. And well, in the more general case of Sasakian manifolds, of course, these notions are defined in terms of Chern classes, but for eta-Einstein manifolds, they reduce to the stated inequalities. So we can say something like that. And of course, an important thing is that the homothetys preserve these positive, null, and negative eta-Einstein manifolds. So if we start, for instance, with a positive, we can deform to another positive Sasakian eta-Einstein. And just a few things about the positive case. This family include the very well-known Sasakian Einstein manifolds, when the manifold is Einstein, like in the Riemannian case. And well, there is a whole chapter of the book of Boyer and Galicki dedicated to Sasakian Einstein manifolds, also a paper by Sparks. And these are more restrictive than the other cases, because from Bonnet-Myers, one can see that a manifold admitting a positive eta-Einstein structure is compact and has a finite fundamental group. So there are more abstractions in this case, but nevertheless, there are many examples of Sasakian Einstein. For instance, recently, these three authors have proved that there are infinitely many families of Sasakian Einstein matrix on every odd dimensional sphere with dimension at least 5. So with these notions of positive, null, and negative, we can rephrase theorems A and B. And for instance, in theorem A, the constants which appeared were these two, and these two are greater than -2. So we obtain that if we consider a product of two Sasakian manifolds, then possibly after possibly applying a homothety to the Sasakian structures, we can say that the product admits a Hermitian structure of the form JAB-GAB, such that the Ricci Bismut tensor vanishes if and only if S1 and S2 are positive, since in these two cases the constants are greater than -2. So the only case working here is when we start with positive Sasakian eta-Einstein manifolds. And for theorem B, well, again, the same. We assume first that the dimensions n2 and n2, n1 and n2 are greater than or equal to 1. And then after possibly applying one of these d-homotheties to the Sasakian structures, we obtain that M admits a CYT Hermitian structure of the form JAB, GAB, if and only if S1 and S2 are eta-Einstein. And well, here the analysis was more complicated, but in this case, we can have S1 positive and S2 arbitrary, could be a positive, null or negative, and S1 is negative or null, and S2 is positive. And well, when one of the Sasakian factors is one-dimensional, the CYT condition reduces to the other eta-Einstein factor being positive. Okay, this always have a possible deformation, but in the case of two Sasakian Einstein manifold or two positive ones, there is no need to perform any deformation. We can solve directly for A and B and find a CYT structure on the product. Okay, to finish, let me mention some examples. For instance, on three-dimensional Lie groups. According to Geiges, a three-dimensional compact Sasakian manifold is diffeomorphic to a quotient by a uniform lattice of S3, the Heisenberg tree group, or the universal cover of SL2R, where here we are identifying S3 with SU2. And these three model geometries correspond precisely to positive S3, null the Heisenberg, or negative the cover of SL2, Sasakian eta-Einstein structures. So each one, for instance, of the Lie algebras of these carry an positive, null, or negative Sasakian eta-Einstein structure. So using theorems A prime and B prime, the rephrased ones, we obtain, for instance, on S3 cross S3, the product of the structures. But this structure is already well known, is known to be Bismuth flat. So of course it is the Bismut-Ricci and the rho and the Bismuth rho is equal to 0. But so this is not a new example. But in the case of CYT, we obtain, because there were more possibilities, we obtain combining these three models. We obtain some CYT Hermitian structures, and of course these structures pass on to the quotient, so we obtain compact manifolds satisfying well quotients of S3 cross S3, the Bismut-Ricci equal to 0, and compact CYT manifolds in all other cases. And well, in higher dimensions, the general Heisenberg group carries, one can see that this carries a left invariant null eta-Einstein structure. So we can combine it with S3 and obtain a CYT structure on these two products. And again, well, we can obtain compact CYT manifolds. For the case of positive, well, it is easily seen that using Bonnet-Myers and results by But-B and Wang, that there is only one example of a positive eta-Einstein Lie algebra, which is SU2. And we don't know yet another examples of negative eta-Einstein structures on Lie groups, which admit lattice, of course, besides the universal cover of SL2R. For instance, this work of Andrada, Fino, and Bezzoni, they prove that the only 5-dimensional Sasakian eta-Einstein whose associated simply connectedly group admits lattices is the Heisenberg, which is null. So maybe we should see in higher dimensions. Okay, and to finish, in the case of positive eta-Einstein, to mention some more examples, okay, what Tano was the first to observe that the unit tangent bundle of Sn has a homogeneous Sasakian Einstein structure, in particular this manifold S2 crosses 3. And well, over the last decades, people obtained, for instance, in dimension 5, positive eta-Einstein structures on connected sums of S2 crosses 3 and infinitely many rational homologies 5 spheres, and also in higher dimensions. Well, another interesting family is these 3 Sasakian manifolds, which are defined as Riemannian manifolds whose metric cone is hyper-Kähler and happens in dimension 4n plus 3. So with our theorems, we could say that the product of any of these 2 manifolds admit this Hermitian structure satisfying Ric B equal to 0 or CYT condition, choosing properly the values and maybe applying the homothéty. And just to mention, to finish, another construction that furnishes many examples of eta-Einstein metrics, especially negative and null, appear on links of isolated hypersurface singularities, which the details of this construction can be found in many places. For instance, the book of Boyer-Galicki, a paper by Boyer-Galicki Mazzeo, and also the presentation by Sparks. And okay, that was all, and thank you very much.
Okay, Alejandro, thank you very much for the nice talk. Are there any questions?
Maybe a quick question.
Yes.
Is anything known about the Chern-Ricci form for these metrics?
Well, maybe we haven't considered Chern, but yeah, could be interesting. Probably there is something, yeah. We should check, yes.
I was going to ask also the Gauduchon ones, but if you haven't checked Chern, then maybe you haven't considered Gauduchon. Interesting. Yeah, thank you.
Oh, thank you for the question. Yes.
More questions? Okay. If not, we thank Alejandro again. Thank you very much, Alejandro.
Thank you.
Thank you.